Swayam Prabha. Digital India. Educated India.
Good morning and welcome to the lecture number 15 of the course Stochastic Hydrology. If you recall, in the last lecture we continued our earlier discussion on frequency domain analysis. We introduced the spectral density function, and then in the last lecture we solved an example starting with the monthly stream flow data, and then we plotted the correlogram for the monthly stream flow data. We examine from the time series plot and the correlogram that there are periodicities indicated in the data. So, the monthly data, time series data, when we express in the frequency domain and carry out the spectral density analysis, the line spectrum as well as the power spectrum show prominent peaks in the spectral densities, indicating that the periodicities that were shown up by the correlogram as well as the time series plot are indeed present in the data. So, the spectral analysis actually brings to the fore the periodicities present in the data, and through the example we could see that the periodicities in the monthly data that we considered were present at a period of 12 months, 6 months, 4 months and 3 months. How do we identify this? We look at the spikes provided in the line spectrum or the power spectrum, the associated W value, the omega value, we convert that into the corresponding periodicity, that is 2 pi by Wp. So, we identified that there were periodicities corresponding to 12 months, 6 months, 4 months and 3 months for the monthly stream flow data that we considered. Then in the same example, we also could see how many of these periodicities are in fact statistically significant. So, we introduced a statistical test by which you can examine the periodicities that you identify through the spectral analysis, whether those periodicities are statistically significant or not. In the same example, what we then did is that we converted the stream flow data to a standardized series by deducting the mean of the associated month and by dividing by the standard deviation of the corresponding month, and then carried out the same analysis of correlogram, of plotting the correlogram and the spectral density function. We saw that the periodicities that were shown in the original data were absent in the standardized data. Then we also introduced the ARIMA models. Subsequent to that example, we introduced the ARIMA model, how to formulate the ARIMA model. If you recall, we said ARIMA model, that is the autoregressive integrated moving average model. So, you have the autoregressive terms and the moving average terms, and the term I there indicates the order of differencing. In discussing the ARIMA models, we also introduced the concept of partial autocorrelation. If you recall, the partial autocorrelation indicates the relationship between the dependent variable, let us say x t, on the independent variable x t minus 1 or x t minus k, let us say if you are looking at lag k, when its dependence, that is x t's dependence on all other terms are partialed out or removed out. So, this indicates the partial autocorrelation. The partial autocorrelation, in addition to the correlogram and the spectral analysis, gives some other information that is present in the time series. The time series plot itself, the correlogram, the spectral density and the partial autocorrelation function, all of these together will tell us which kind of models are useful for the particular data. So, in today's lecture, we will continue with that discussion and see how we formulate the ARIMA models, autoregressive integrated moving average models, and perhaps how we identify which type of models, how many terms in the model AR model needs to be included, how many of AR terms need to be included, how many of MA terms need to be included in the model for the specific application in question. In the last lecture, I just mentioned that these are the type of models that I will be covering in this course are called as the Box-Jenkins time series models, and they are valid. The coverage that we will do in this course is only meant for stationary time series. We do not cover the non-stationary time series, and therefore, your original time series, if it is non-stationary, you must first convert that into a stationary time series, which means first you have to identify whether the series that you are considering is stationary or non-stationary. If you look at the correlogram, if the series is non-stationary, then the correlogram decays rather slowly, whereas if the stationary in the case of stationary time series, the decay is quite fast. For example, here I have shown a correlogram of a stationary time series, the decay is quite rapid, whereas for the case of non-stationary time series, the decay is rather slow, indicating that the dependence does not die down quickly, and therefore, it becomes a non-stationary time series. So, the first indication is of non-stationarity is if the correlogram does not die down fairly rapidly, then you must suspect non-stationarity in the data. Then we must have the wherewithal or the means to remove the non-stationarity and convert the time series that you have into a stationary time series, only then apply the type of models that we will be discussing now. One way of removing the non-stationarity is by standardizing the time series. In the example that we saw in the last lecture, we saw that once you remove the once you standardize the series and plot the spectral density as well as the correlogram, it indicates that there is no correlation present in the data, or the data becomes random and the series becomes stationary. So, one way of doing removing the non-stationarity is simply standardizing the time series. But in the ARIMA models, we also consider what is called as the differencing of the time series, first order differencing, second order differencing, etc., which I will introduce presently. This is a simple way of removing the periodicities and making the time series a stationary time series. Not only the periodicities, if you have trends can also be removed by differencing. So, in general, we use the differencing to convert the non-stationary time series into a stationary time series. What I mean by differencing is that if you have a series x t, you take the first difference, that means x t minus 1, just deduct the previous value and compute the new series y t, constitute the new series y t. So, if you have x t minus 1, that means the first order differencing, where you are simply deducting the previous term, this is called as the first order differencing. What does it do? For example, if you have a series like this 2, 4, 6, 8, 10, 12 and so on, if you plot x t versus t, you have an increasing trend in the data 2, 4, 6, 8 and so on. Let us say I do the first order differencing here, then what I will get 4 minus 2, 6 minus 4, 8 minus 6, 10 minus 8 etcetera. So, the new series will consist of 2, 2, 2, 2 and so on. So, if you plot now y t versus t, you have a horizontal line, this is obviously stationary. So, what was originally non-stationary, just by first order differencing in this particular example, we have converted into a stationary time series. So, in general the differencing has the effect of removing now some amount of non-stationarity in the data. Why I say some amount of non-stationarity is that in this particular case all the non-stationarity has been removed, but in the actual data when we are considering let us say stream flow at a particular location and so on, depending on the strengths of the periodicities and the strength of the trend etcetera that are present, the nature of the trend, nature of the periodicities that are present. Not all the non-stationarity may be removed just by the first order differencing. Maybe you will have to go to the second order, third order etcetera. Even then it may not be possible to remove the complete non-stationarity in the data, in which case we try other methods, for example, standardization and so on. As we explained in the previous lecture, the presence of non-stationarity in the data can be examined by various statistical tests. So, once you do the differencing and constitute the new time series, on the new time series, newly constituted time series by differencing, you again do the analysis of correlogram and then the spectral density and spectral analysis and so on, to examine whether this series that you constituted now is in fact stationary. When you achieve a satisfactory degree of stationarity, then you can use the type of models that we will be discussing in the course. So, similar to the first degree of first order of differencing, you also have second order of differencing, where you take the first difference of the difference series itself. The x dash t here is x t minus x t minus 1. So, x dash t is the first order differenced series. In the second order differencing, you take the differencing on the already difference series. So, x double dash t, which is the second order differencing, is given by x dash t minus x dash t minus 1. So, if you write like that, if you write it in a long form, so what is x dash t? X dash t is x t minus x t minus 1. This is the first order differencing on x t, and minus x dash t minus 1 is the first order differencing on x t minus 1, which is x t minus 1 minus x t minus 2. You are taking the first order differencing on x t minus 1, which means this would be x t minus 2 x t minus 1 plus x t minus 2. So, x double dash t, which is the second order differencing, can be written as x t minus 2 x t minus 1 plus x t minus 2. Like this you can carry on the third order differencing, fourth order differencing etcetera. In general, in hydrology, most hydrologic applications where we are using autoregressive moving average type of models, we go typically up to the second order differencing, not more than that. Let us look at one example here. Let us say you have this time series, this is the same time series that we considered earlier. For 12 months I have shown here x t, these are the observed values, let us say observed monthly stream flow values. You take the first differencing, so x t minus x t minus 1, you get minus 270.8. Then x t minus x t minus 1 here, that is x 2 minus x 3, you get minus 184.1. x 3 minus x 4, you get 410.1 and so on. Like this you get the first order differencing. Then for the second order differencing, you do x dash t minus x dash t minus 1, which means x dash 2 minus x dash 3. So, you get minus 86.7, because these are both are negative. Then this minus this, that is minus 594.2 and so on. So, you get the second order difference series. So, like this, from the original series you can get the first order difference series, second order difference series and so on. Then you can examine whether this series that you obtained by first order differencing is in fact stationary, or this is a stationary. If this is non-stationary still, you go on to the higher order difference series and examine whether this is stationary. If you are still not satisfied, then you go to the next order of differencing, which is the third order differencing in this case, and then examine whether that is stationary and so on. Obviously, I have shown only 12 values here, but this has to be done for a longer series. Typically, we may have monthly data for about 50 years, 60 years etcetera. On that series, you have to do this tests of stationarity or lack of it. Now, we will consider the same data that we considered in the example on spectral analysis. So, there are 348 values, only 12 values I have shown here. So, this is between 1979 and 2008, this is monthly stream flow data. So, you have n is equal to 348, only part data is shown and the time series plot etcetera is shown earlier. So, this is the time series plot that you have for 348 values. We have also shown earlier the correlogram for this as well as the spectral density for this. The correlogram indicates that there is a significant periodicity present. I again repeat that right from the time series plot, you suspect that there is a periodicity, because just if you look at the time series plot, there is a regular pattern. The flows are increasing and then decreasing and so on in a fairly good regularity. And that information is also seen in the correlogram, which indicates that there is a periodicity present in the data. We want to verify this and pinpoint exactly where the periodicities are present, and therefore, we convert this into the frequency domain and carry out the spectral analysis, plot the line spectrum or the power spectrum, which brings out the spikes, and these spikes correspond to the periodicities. And this periodicity is of 12-month periodicity, and this is 6 months, and this is 4 months, and this is 3 months. Which means that we have now seen that this time series that we are considering is not stationary time series, because there are significant periodicities present in the data. Why do I say significant? Because we also examined for the periodicities that were identified in the spectral analysis corresponding to 12 months, 6 months, 4 months, 3 months, all of them were statistically significant. Recall that we formulated a statistic corresponding to these and then compared it with the F distribution with 2 degrees of freedom, and then concluded that all the periodicities that we identified here are in fact statistically significant. Now, the question is, if you want to apply the time series models which are meant for stationary time series on this particular time series, which you know is in fact non-stationary because of the presence of significant periodicities in the data, then you have to convert that time series into non-stationary into a stationary time series. So, let us see what happens if you do the first order differencing on the time series that we had considered. So, what is first order differencing? It is simply x dash t minus that is x t minus x t minus 1. So, let us look at what happens here for the first order difference data. So, in the original data which is shown here, all I do is take x t and deduct x t minus 1. So, I formulate a new series x dash t as x t minus 1. So, corresponding to the original series, you have a new series now, and that series I plot here. So, this is the time series of the first order difference data x dash t. I plot this time series, which is different from the original time series like this, but still you see some kind of a pattern here, that is the values are increasing periodically, increasing with some regularity and then decreasing with some regularity and so on. The corresponding correlogram appears like this, again indicating that there are still periodicities present here, and the line spectrum appears like this. The original line spectrum was like this. So, the line spectrum is no different, not much different in terms of its indication of the periodicities. So, the first order difference data still indicates that there is some non-stationarity present in the data. We will go to the second order differencing now. What do I do in the second order differencing? I take x dash t minus x dash t minus 1. Now, when I do the same analysis on the second order difference data, the time series appears like this, which is different from what was there for the first order difference data. The correlogram appears like this, still indicating that there are significant periodicities that are present in the data, and the spectral density, this is the original spectral density here, and this is the spectral density for the difference data. It again indicates that there may be some periodicities. Of course, we need to test for the significance, statistical significance of these periodicities, but there is an indication that the time series that you so formulated by taking the second order differences still is not devoid of periodicities. And let us examine what happens in the third order differencing. So, because we are not satisfied with what we did in the second order differencing, we go to the third order differencing. What do I do in the third order differencing? I take x double dash t minus x double dash t minus 1. So, in the first order we take x t minus x t minus 1, in the second order we take x dash t minus x dash t minus 1 by and this we call it as x double dash t, which is the second order differencing. In the third order differencing, I do the difference on the second order difference series, which is x double dash t minus x double dash t minus 1. That is, I will take the difference on this difference series itself. When I do that, I get the third order difference series. You get the data like this, the time series data like this, and the correlogram is like this. Again, it indicates these are the 95% significance lines. Recall that the 95% significance lines you form by taking plus minus 1.96 by root n, and for most practical purposes you take 2 by root n, that is plus minus 2 by root n, where n is a number of sample data, in which in this case it is 348. So, these are your significance bands. So, it indicates still that there are still periodicities present here, and even the spectral density shows that there are periodicities present in the data. Again, for comparison, this is the original spectrum here, and this is your new spectrum. In the original spectrum, you had a spike corresponding to 0.53 or something, indicating a periodicity of 12 months, but that is absent here, whereas the spike corresponding to 1.2 or around that is still present, and these two have come up now. Corresponding to 2.2, the spike has become more prominent in the third order difference data. As we saw in the example that I discussed in the spectral analysis, the fact that these are prominent spikes does not necessarily mean that these are statistically significant periodicities. We need to examine for the statistical significance of these. It may so happen that these are statistically insignificant, but however, you are seeing from the correlogram as well as from the spectral analysis that the periodicities are not entirely removed, especially because the correlogram shows that there are significant correlations still present in the data, and therefore, it indicates that the periodicity may still be present in the data. And therefore, now let us see what happens if we do the standardization on this data. If you do the standardization, you may perhaps end up with a completely random series devoid of any periodicities. Of course, with the third order differencing, you may have significant correlations which you may use in the models, because you are talking about correlated data when you are looking at time series models. In doing standardization, essentially what we are doing is you are taking out the mean, you are deducting the mean and dividing by the standard deviation. So, if you look at the standardized data, z dash t is equal to x t minus x t bar, x I bar minus s I. Recall that this I is the month corresponding to the time period t. So, in this case t goes from 1 to 348 and I goes from 1 to 12. So, corresponding to every t you have an association with the particular month in the year, and you are taking out the particular mean of that month and dividing it by standard deviation of that month. When you standardize the series, you will see that the time series looks more or less random like this, and most of the correlations are all insignificant. There is hardly any correlation that is outside the significance bar except for the first one, and the line spectrum shows that the data is random. So, there are no specific spikes here which are much different from the other spikes. Compare this with the original spectral density, you see that this spectral density indicates much more random data corresponding to in comparison with the original data. So, standardization for the data indicates that by standardizing we have removed the periodicities present in the data. Now, we can use the time series models on the standardized data, or you can also use on your third order difference data if you are sure that by doing this you have removed these periodicities. That means, the periodicities that are coming up now are statistically insignificant. So, you could use the ARIMA type of models on the third order difference models, where the order of differencing is third order. Now, we introduce another important concept. So, what did we do now? We saw methods by which you can remove the trend or the periodicities present in the data by differencing, first order differencing, second order differencing, and so on. The presence of the periodicities, let us say that even after differencing you still have certain periodicities present in the data, indicating that there are certain lagged correlations at particular lags which are still quite significant. Now, these can be addressed by ARIMA models by introducing those particular lagged terms. I will discuss this in greater detail later on, where we are talking about contiguous and incontiguous ARIMA models, where specific terms can be included without including the previous terms. Anyway, right now we will not worry too much about it, but right now what we will do is we will introduce an interesting operator called the operator B, which is useful in writing down the ARIMA models in more compact and elegant forms. The effect of the operator B is to shift the argument to that one step behind, simply shift it one step behind. For example, when I use the operator B on x t, it is simply equal to x t minus 1. When I use the operator B on x t minus 1, it is simply x t minus 2. So, the operator B shifts the argument to one step behind, that is all. Now, this becomes a very handy tool in expressing the various ARIMA models in more compact and elegant forms. Say for example, you have the AR1 model, autoregressive model of order 1. It is written as x t is equal to phi 1 x t minus 1 plus epsilon t. This is our original AR1 model. So, I will use the B operator now. So, x t is equal to x t minus 1, I will write it as B x t. So, phi 1 into B x t plus epsilon t, that is x t is equal to phi 1 B. So, I will take all the x t terms on one side. So, I will write it as x t into 1 minus phi 1 B is equal to epsilon t. So, 1 minus phi 1 B becomes the term for AR1 component. So, we are saying x t into the AR1 component is equal to epsilon t. Let us say we want to write for AR2 model. What is AR2 model? It is x t is equal to phi 1 x t minus 1 plus phi 2 x t minus 2 plus epsilon t. So, now I will use the B operator. Wherever there is a x t minus 1 term, I will put B into x t, and x t minus 2 term I will put it as B into x t minus 1. So, I will write this as x t is equal to phi 1 B x t, this B x t is x t minus 1 plus phi 2 B x t minus 1, x t minus 2 is B x t minus 1 plus epsilon t as it is. Now, I will further expand, x t minus 1 is B into x t. So, I will further expand this. So, this is phi 1 b into x t plus phi 2, this was b x t minus 1. So, I will write that as b into b x t, because x t minus 1 is b x t. So, together I will write this as b square x t, that has to be x t there. So, this is x t, b square x t plus epsilon t, and therefore, I will write it as x t into 1 minus phi 1 b minus phi 2 b square is equal to epsilon t. So, we write the AR models as x t into some term in terms of b and in terms of the associated parameters, and on the right side we keep the noise term epsilon t for the AR models. So, this becomes the AR 2 component. Compare this with the AR 1 component, this is 1 minus phi 1 b, and for the AR 2 component 1 minus phi 1 b minus phi 2 b square. So, in general you can say, you can write it as x t minus x t into, look at this, for the second term what we have 1 minus, for the second term I is equal to 1 to 2 of phi I b to the power I. So, for a pth model we can write for the pth order AR model, we write this as x t into bracket 1 minus summation I is equal to 1 to p, so many terms of the AR model, phi I, phi 1, phi 2 and so on here, b to the power I. So, b to the power 1 plus b to the power 2, negative is outside of the summation, and right side is epsilon t. So, this is how we express the AR model in a more compact form using the B operator. So, anytime you see the models expressed like this, you immediately must relate it with AR models, and the order of the AR model is given by how many terms you have in this. So, there are p terms here for an AR P model. Now, recall that we said autoregressive integrated moving average models. What we explained so far was AR models, that is you do not have differencing, you do not have MA terms, MA terms is moving average terms. So, these are ARIMA, if you want to write it in the general form, ARIMA P 0 0, that means there is no differencing involved, there is the order of differencing is 0 and there are no MA terms involved, therefore, the order of MA terms is 0. So, ARP model is ARIMA P 0 0. In general, we write the ARIMA model as PDQ, ARIMA PDQ. It means that you have corresponding to autoregressive, you have P number of terms. The order of differencing is denoted by D and the number of moving average terms is Q. So, ARIMA PDQ indicates AR, you have P number of terms of AR, the order of differencing is D and the number of MA parameters is Q. So, this is the general notation that we follow for any ARIMA model. Given a time series x t and the given the order of differencing, first you do the differencing on the time series of that particular order and then apply an ARIMA model. What do I mean by ARIMA model? ARIMA model is with 0 differencing, that means you will have ARIMA P comma Q. So, first you do the differencing and then write the associated ARIMA model. We will discuss this through some examples later on subsequently in the lecture, but we will continue our discussion on how to apply the B operator. So, let us say that you have a autoregressive moving average model, that means you have done the differencing already or there is no differencing, you are simply writing the AR parameters and the MA parameters. So, you have P of AR parameters, P number of AR parameters and Q number of MA parameters. So, a general ARIMA PQ model is written as x t is equal to phi 1 x t minus 1 plus phi 2 x 2 minus 2 x t minus 2 etcetera. There are p terms. So, phi p x t minus p plus there are q number of moving average terms. The moving average in the context of ARIMA models is not the same as the moving average that we discussed earlier when we were talking about taking averages in the windows across which is moving across the time series. This has a slightly different connotation here. We talk about moving average in the context of the residuals that result from the model. So, this is you have q number of moving average terms theta 1 E t minus 1 plus theta 2 E t minus 2 plus etcetera theta q E t minus q. So, you have q number of moving average parameters theta 1, theta 2 etcetera up to theta q, and you have p number of autoregressive parameters phi 1, phi 2 etcetera phi p plus the noise term or the residual term E t. Now, remember see here notice that E t minus 1, E t minus 2 etcetera up to E t minus q is what you have written for x t. So, when you go to x t plus 1 for the next term, this E t gets into the MA parameters here, and then you will have a term of E t plus 1. When we do the numerical example, it will be clear of how we account for the residuals in the moving average terms. Now, these are in fact the residual terms that you have here are in fact important in examining whether the model that we have fit to a particular data passes all the tests or not. So, we need to do the statistical tests on the residual series after we fit the model on a particular time series. Let us say you have the stream flow for every monthly stream flow for last 50 years data, and then you have estimated the parameters and then fit the model, and then you get the residual series. On the residual series you need to do the tests. The assumptions that are involved in this model are that the series of residuals, it has a 0 mean and they are all uncorrelated. In the numerical example, we will show how to do the tests on the series of residuals that you get. So, this is how a general ARIMA PQ model is written. You have p parameters, p terms of autoregressive terms, and you have q terms of moving average terms plus the noise epsilon t, E t or epsilon t. Let us see how we express this using the difference using the B operator, for which let us say you are talking about a term of first order differencing x t minus 1 is equal to E t. This is your what is the model here? You have only integration, you have neither the AR terms nor the MA terms. So, you have only the integration, which means in our ARIMA P d q notation, what does this mean? P is 0, Q is 0 and D is 1. So, you are only doing the differencing on the series. So, x t minus 1 is equal to E t if you write like that. Okay, for clarity let me write it down. So, this is nothing but ARIMA P d q, or P is 0 here, you do not have any AR terms, D is 1, you are doing the first order differencing, and Q is 0, there are no MA parameters. So, this is ARIMA 0 1 0 model. How I would have written x t is equal to x t minus 1 plus E t, that is all. So, you are doing the differencing here. Now, let me express this in terms of the B operator. So, x t minus 1 is B into x t will be equal to E t. So, you are putting the operator B on x t to get x t minus 1, that is x t into 1 minus B is equal to E t. So, this is how the first order differencing looks. Let us see how the second order differencing looks. Let us say that I am not writing any ARIMA model here, I am simply looking at the second order differencing. I want to express this in using the operator B. So, this is x double dash t, which is the second order differencing, is equal to x dash t minus x dash t minus 1, the second order differencing. What is x dash t? It is the first order differencing. Therefore, I will write this as x t minus x t minus 1. And what is x dash t minus 1? It is x t minus 1 minus x t minus 2, that is the first order differencing on x t minus 1. So, this will be x t minus 2 x t minus 1 plus x t minus 2, that is x t minus, what is x t minus 1? That is b into x t, plus what is x t minus 2? X t minus 2 is b into x t minus 1, and x t minus 1 there is again b into x t. Therefore, this will be b square x t. So, if you take out x t outside, what you are left with? 1 minus 2 b plus b square, which is 1 minus b the whole square into x t. So, the first order differencing was x t into 1 minus b. The second order differencing is 1 minus b whole square into x t, that is x t into 1 minus b, here x t into 1 minus b the whole square. If you take the third order differencing and do the same exercise again, you will get x t into 1 minus b to the power 3, fourth order x t into 1 minus b to the power 4, and so on. So, in general, the dth order difference which we need for ARIMA PDQ models, in general the dth order differencing can be expressed as x t into 1 minus b to the power d. So, this is how we get the dth order differencing in terms of the operator b. Let us look at the ARIMA 111 model. That means, the first order differencing is done on the series and then you apply the ARIMA 11 model. So, as I said, any time you have the order, there is a differencing order present, that is any time when d is not equal to 0, first you carry out the differencing on the original time series. So, we first carry out the differencing of this order. So, this is first order differencing. So, y t is equal to x t minus 1. I will constitute another series now, which is a first order difference series, and then apply the ARIMA model of order 1 1 on the series y t, on the difference series y t. So, I write y t is equal to x t minus 1 and then write an ARIMA model with one AR term and one MA term. So, on y t I write this as y t is equal to phi 1 y t minus 1 plus theta 1 E t minus 1 plus E t. So, you have one AR parameter and one MA parameter plus the noise term here, and this you are writing it on the difference series y t is equal to x t minus 1, and this difference order is 1 here. If you had an order 2, first you reconstitute the series y t by taking the second order difference, and then you write the ARIMA model on the difference series that you obtain. So, first you carry out the differencing and then write the ARIMA model on the difference series. So, now we will use the B operator to express this model. What is y t? Now, I am just expanding. Y t is x t minus 1 is equal to phi 1 into x t minus 1 minus x t minus 2, because y t minus 1 is here, plus theta 1 E t minus 1 as it is, plus the noise term epsilon E t. X t minus, this I will write it as x t minus 1 is b x t is equal to phi 1, x t minus 1 is b x t minus x t minus 2 is b square x t as we have done earlier, plus theta 1 b E t. Remember, the B operator operates on any of the terms and it simply shifts the particular argument to one time step behind. So, when B operator operates on E t, you get E t minus 1. So, I will write E t minus 1 as theta 1 b E t plus epsilon E t as it is. So, collecting all the terms on of x t on the left side, you write x t is x t into 1 minus b minus phi 1 b plus phi 1 b square is equal to E t into 1 plus theta 1 b. That is how you express an ARIMA 111 model. So, given any ARIMA PDQ model, you should be able to use the B operator and express this in a more compact and more elegant form using the B operator. Okay, now we now know that given the time series, first you identify the order of differencing that you would like to do, either the first order differencing, second order differencing and so on, and then identify the number of AR parameters and the number of MA parameters, and therefore, you will have a particular model ready with you. So, you have this kind of model. So, given any structure of ARIMA model, you now know how to express that ARIMA model in a compact form like this using the B operator. Now, we will address the question of, given the time series of a particular variable, how do we identify which of these large number of models fit that particular time series, or which among these large number of models can we use to represent the particular time series. What I mean by that is, in the general form ARIMA PDQ, you virtually have infinitely many models possible. P can vary from 1 to let us say 20, 25 and so on, although there is you can keep on going depending on the data. Then similarly Q, MA parameters, theoretically you can keep on going 1, 2, 3, 4, 5, 6 and so on. So, and the order of differencing, first order differencing, second order differencing, etc. So, virtually you can theoretically form infinitely many number of models using this general structure. So, for a given time series, which among these infinitely many possible models are in fact feasible or can be used for the given time series is the primary question that we need to answer. Now, in the Box-Jenkins type of analysis, we follow three primary steps, three major steps, namely identification of the model structure, that is PDQ, how many terms of P, how many terms of D, that is which order of differencing, and how many MA terms that you would like to include. So, first you identify the model structure. Then once you identify the model structure, let us say that you have identified that there is one AR term, one order of differencing and one order of MA term. Then you are left with the problem of estimating the parameters. You have a parameter phi 1 here, you have a parameter theta 1 here in this particular case. So, in general for ARMA PQ model, for example, you will have P parameters to estimate for the AR terms and Q parameters to estimate for the MA terms. So, once you write the model structure, you come with the second question of parameter estimation. So, you need to estimate the parameter and then calibrate the model. What do I mean by the calibration? That for the data you will have the residuals that arise from the data by applying this particular model that you have identified, and those residuals must satisfy the assumptions that we have made for the residuals, namely that they should have a 0 mean and they should all be uncorrelated. They should constitute a series with uncorrelated values. Then we do the model testing on the remaining data and the validation. So, these are the primary three steps. One is identification, model identification, another is parameter estimation and calibration, and third one is model testing or validation with the remaining part of the data. So, typically what we do is, if you have a series of let us say 50 years of monthly stream flow data, how many values you have? 50 into 12, 600 values. Typically you build the model on the first half of the data, take n by 2 values and fit the data, do the calibration etc., and do the validation on the remaining part. Depending on the length of the data, this can be either n by 2, that is you build the model on n by 2, or if the data is fairly small, then you do not have an adequate number of values on n by 2, and therefore, you may have to go with 3 n by 4 or 75% of the data you use to build the model and the remaining part to test and validate the model. All these nuances of model building we will discuss when we show the applications and case studies and so on, where depending on the length of data you may have to sacrifice on the validation part and validation amount of data that is available for validation and so on. So, you do not have to be really strictly bound by always going by n by 2 for model building and model testing and so on. It actually depends on the length of data that you have, and as I mentioned right at the first right in the first lecture, in hydrology mostly you are constrained by the length of the data that is available to you. So, identification of the model structure, which means we need to see how many of the autoregressive models autoregressive terms to be included and how many moving average terms and what level of differencing that you need to do and so on. So, as I mentioned, the first step in identification of the model is examining if the series that you have is stationary or not. So, you plot the correlogram. If the correlogram shows a very slow decay, either you may have sinusoidal correlations, or the correlogram indicating sinusoidal variation, or it may have a slow decay, either exponential decay or normal nonlinear decay. If you have a slow decay, then it indicates that the series is not stationary. Once you identify that the series is non-stationary, then we need to make the series stationary for use of the ARIMA models. So, we may adopt like I just demonstrated, you may adopt differencing, that is first order differencing, second order differencing, etc., to make sure that you remove non-stationarity. Then you obtain the order of AR and MA components for the model. So, once you difference it, then you obtain the order of AR and MA components. The partial autocorrelations that we discussed in the last lecture, we introduced in the last lecture, is a very handy tool for identifying the AR components. If there are significant partial autocorrelations present in the data, let us say there are only 2 significant partial autocorrelations present in the data, it indicates an AR model of 2 may be appropriate for the particular time series, provided it also satisfies certain conditions on the that is correlogram. So, if you want to identify just the AR components, you have to look at both the correlogram as well as the partial autocorrelations together. If your the correlogram shows a decay and the partial autocorrelations show significant presence of 1 or 2 or maybe more partial autocorrelations which are significant, then it indicates the AR terms to be of that order. Let us say you may have AR2 or AR3 depending on how many partial autocorrelations are significant or not. Now, this discussion on identification of exactly how many AR terms and how many MA terms to be included has significance only when you want to shortlist on a few models and then examine which among them are more appropriate for your particular application and so on. We will continue this discussion in the next lecture of how to identify how many of AR terms and how many of MA terms are appropriate for the particular situation. So, to summarize then, in this lecture we discussed how to formulate the ARIMA models, the general formulation of ARIMA models, and how to do the differencing, the first order differencing, second order differencing, and what effect the differencing has on removal of periodicity. So, we tested with one numerical example that the time series that we considered had significant periodicities present. Then we did the first differencing, second differencing, third differencing, etc., whereby we saw that the series becomes, the periodicities are removed as we keep doing the differencing. We also saw that standardization removes periodicities. So, on the same time series we did the standardization. By standardization I mean ZT, which is a standardized series, we express it as XT minus XI bar by SI, where XI in the case of monthly time series, XI is the mean, XI bar is the mean of the particular month's flow to which the time T belongs. Then we wrote the ARIMA models using the B operator. So, B x t is equal to x t minus 1. So, the effect of the B operator on any argument is simply to shift the argument one time step behind. So, we examined how to write a general ARIMA model using the B operator in a more compact form. Then towards the end of the lecture, we have just listed out the steps that are involved. One is identification of the model, by which I mean identification of how many AR terms and how many MA terms, and what is the level of, what is the order of differencing that you need to do. So, this gives the identification of the structure of the model. Then we do the parameter estimation and calibration in the second step, and in the third step we do the validation and model testing. So, in the next lecture we will see details of each of these three steps. How do we identify, how do we estimate the parameters, and how do we do the testing. So, we will meet in the next lecture. Thank you very much for your attention.